And now for our next speaker, it's a pleasure to introduce Eleonora Brembilla, and she's assistant professor at Delft University of Technology here in the Netherlands. She's in the Faculty of Architecture, and her expertise is in the area of daylight modeling and monitoring. And within this large body of work, she's looking at annual daylight simulation, weather files, solar radiation data, and operational daylight performance. And Dr. Brembilla will be talking to us about the TU Delft Co-Creation Center, and it's a fully glazed living lab for indoor environmental quality and testing. Thank you and welcome.
Right. Well, thanks a lot, Martha, for the introduction, and thanks to VELUX for inviting me here. It's really exciting to be on this part of the camera. So the presentation I'm going to give you now, it's partly about research findings and results, but they're just the initial results. So the presentation is really mostly about a building and its story and the vision that we have for this building. So the building, in case, is the TU Delft Co-Creation Center, and the vision that we have for it is to transform it into a fully glazed living lab for testing indoor environmental quality. So the building itself is located in the TU Delft, in the middle of the TU Delft campus. And in a moment, the slide should change. Yes. So the building itself, as I said, it's in the middle of the TU Delft campus, and it's part of the Green Village, which is an area dedicated to field research in the built environment, and is basically an innovation park that hosts many different types of buildings that are actually used by people, and where research and technology can go on at the same time and really push the boundary of what we know about living conditions. So we have some residential building, an office building inside the Green Village, and the Co-Creation Center, which is a small size conference center for about 130 people. And this building went through several design transitions, several design concepts from its initial concept development. And as you can see here, at some point, there was also a solar chimney planned for the building itself. And then, yeah, plan changed a little bit through the design process, but what really remained at the core of the Co-Creation Center building is its transparency. So transparency was really there at the very beginning and is still there now that the building has been constructed. So that was a strong point that the architect wanted to give to the design, the capability to see through the building from all sides, from all the sides of the building, and to have this like floating rooftop laid on a transparent, almost non-existent wall box. So here at the front, you can also see the space that is reserved for the services and facilities, which is a no-no house, but the rest of the building is really completely transparent all around. And as it was developed and as the concept was put together by different research groups, everyone took this opportunity to add some innovation, some innovative research into this facility. So we not only have research in indoor environmental quality, but we also have, for example, the use of recycled concrete for the foundation slab of the building. We have some energy piles that were mounted below the foundation to allow for seasonal storage of it, so store heat that can be accumulated in summer and then reused in winter. Then we have structural glass, that is a key element that allows that complete transparency. So even the column of the building are made out of glass. So you have really like a fully glazed facade. And then in the Nono house that we saw before, there is also the prevalent use of nitrogen-absorbing materials. And then, of course, we have other elements that are more related to the indoor quality, so like wide tunable electric lighting and the acoustic ceiling at the top of the building, and most of all, the climate tower, which is the element that is mostly connected to the research that I'm part of. So the Converge project is a project that is looking at more specifically at the indoor environmental condition of the building, and at all the building systems that are hosted in this climate tower and the rest of the building itself. So the climate tower hosts some PV panel at its outside wall, and those PV panels allow the production of the energy for the building system that are placed inside the tower, like the heat pump at the bottom of it. And then we have also an heat exchanger that recollect heat from the return air and reuse it to warm up the supply air. And then we have also a PCM battery, which are phase-changing material, so material that can either, again, collect or release heat when needed. And then, as you can see from the other side of the slide, we have also automated roof light openings, automated external Venetian blinds, which are the part I'm mostly involved with, and last, mechanical ventilation through the floor cavity. So basically, the fresh air is pulled into the building through the climate tower and then pushed in the floor cavity and up in the building space through perforated panel that makes the floor part. So this is the main collection of building system we have in the climate tower. And the Converge project is aiming at answering this main question. Can a fully transparent building act as a passive building while guaranteeing indoor comfort? And the rationale behind this question and behind the whole research is that if we manage to make this challenging building, this fully glazed building, behaving as a passive building, then chances are that this same solution can be adopted for other type of buildings in a similar, if not the same way. So ideally, we would like to get to this stage by the end of the project, and the main concept to get there is the concept of active passiveness. So this is a concept developed by one of the initiators of the Converge project, Professor Peter Luskure. And by active passiveness, we basically mean that the whole building system components of the building should actively perform their duties in a way that every time optimize the energy consumption up to a point where it's almost null energy consumption, energy demand. So the building is reacting to its environment in an active way, but to favor passive solution. And this is a big challenge. So the combination of all the systems that we saw before should work at unison at the same time for every single moment and every single outdoor condition, try to get to this passiveness state. So it's really like an orchestra. It's really like an ensemble of different performers that needs all the time to communicate to each other and follow a main direction that leads toward the same aim, the same song. So as part of the orchestra, we have obviously the heating system, and we have a cooling system that both work in different way for different season, and sometimes, because we are in the Netherlands and the weather is really, really variable, they can even act together in the same day. And then, of course, we have the ventilation system that has to work all year round and provide fresh air to the occupants. And the solar shading, last but not least, we need to modulate the entrance of solar heat and light. So all these systems together need to talk to each other and, in a way, decide what's the optimum, how to get to the best solution at any given moment. So the big role that we need is the role of the conductor as well from the orchestra. And the way we envision this conductor is practically the use of the digital twin concept. So I hope you still see that. Basically, this digital twin idea can act as the main conductor, for the research. And I know that it's a concept that is being exploited more and more, and that it's sometimes used inappropriately, sometimes more appropriately. And I'll go on. And so I think in this case, it would be a very appropriate use of the digital twin concept. So what a digital twin is a dynamic, up-to-date representation of a physical object or system. And with a complete collection of all data in one place, a digital twin evolves with the flow of real-time input from sensors and more. So the digital twin would be a perfect actor or conductor in this kind of scene, in this kind of scenario, to orchestrate and to direct all the different parts of the building. And the co-creation center is really well equipped to do that, because a digital twin works based on sensors and monitoring data. So all the data that are collected and constantly analyzed by the system can allow that continuous update of the virtual model that work in parallel to the real model. And as you can see here, it's the building is well fitted with all sorts of sensor, and sensor in reality. They're not just fictional thing. They are very real, and it means a lot of cable and a lot of setup to make them all work as we want. And in this specific case, the various sensors that we fitted in are some ceiling multi-sensors recording different parameters from temperature to relative humidity, movement, light levels. And then we have a number of temperature sensors throughout all the building on different surfaces. We have also sensors in the climate tower recording the condition of the supply and the return air. Some sensor looking at occupancy through the doors and the movement of people. And then we have a weather station on the roof measuring outdoor condition. And when I joined the project, I also asked for even more sensors to be fitted in. So I had 5 illuminance sensors placed on the outdoor of the building and 1 inside. So we have 1 now looking up at the full sky dome, and 3 sensors placed vertically on 3 different facades of the building, west, south, and east, and 1 sensor that is usually placed inside the building on top of a tripod that we can move as we need. And to give you an idea of what the different obstruction and outdoor condition around the building are, these are some fisheye images from the same point of view of the sensors. Remember that they are just simple illuminance sensors. They are not, unfortunately, a Skycam or HDR camera mounted in those positions, but I did go on the roof with a fisheye camera and took the images as if it was a viewpoint of the sensor itself. So this is what the illuminance sensor looking up sees, and then we have the view from the west sensor, the south, and the east sensors. And through all this data and some more data about occupancy and activity and outdoor weather condition, we are aiming at controlling the blinds and the visual comfort and the heat, the solar heat in two different ways, with two different control strategies. One control strategy is what we call the energy mode, so a strategy that exploits solar heat to reach the desired energy balance. And the other strategy is the visual comfort mode, so the strategies that prioritize visual comfort over energy harvesting and provide comfortable visual condition for people inside the building. So basically, what we are aiming at is to use data, for example, about the activities that people are performing in the building, or just data about whether there are or not people in the building, and data about external weather conditions to decide which one of these two strategies is the best one to apply at any given moment. And the operation of the blind and the control of the blind through these two different strategies really not only change the performance of the building, but also very much the way people experience the building, the way the building look like. Because it's all fully glazed, the change in the space due to the blind operation is massive. So I'm going to show you 4 slides with this and 3 more that shows gradually how the space look like as you close the blinds. So this one is with the blinds all pulled down but kept at a horizontal tilt. And then we have a more slanted tilt that already block part of the view and make the overall condition a bit dimmer, a bit darker. And then when the blinds are fully closed at the back here, at the back facade, you start seeing some strong reflection from the glass and no view to the outdoor anymore, but the reflection from the other side. And if you close the whole space off, the feeling is really, really different. So you have a completely different perception of this space depending on how you operate blinds. So this is what I started looking at on the building. So following that idea of trying to match the actual real building monitoring data with the simulation data simulated illuminances, I tried to match what we measure from the 4 different outdoor illuminance sensors with what I could simulate at the same viewpoints. And if you look at this scatter plot, you see that the trend is more or less similar to the diagonal line in the middle. There is a lot of scattering and a lot of outliers due to the various factors like the sky model that we use, the sky condition, the reflectance of obstruction and all. But it's already a promising start, at least for the up, south, and east sensor. If you look at the west, there is a group of data that is actually a bit, very off. And so I looked more closely to those one, and I reproduce in simulation the same viewpoint and the same view that the illuminance sensor have. And you can see the stark difference in the west scenery, the outdoor scenery. So in reality, the trees and the obstruction are much, much higher. So if you look here, there is also the sun position highlighted in in the simulated scene. And obviously, that big an obstruction obstructs part of the sky, and we end up with results that are very different between the simulated and the real value. But we know where the problem is, and we can correct for that. The next thing up would be to look at different sky conditions in time. So then looking at different type of sky, from variable type of days and skies, to overcast and to clear skies. So the variable one will be the real challenge, because in simulation we use the parasol weather model that doesn't necessarily model the actual situation that we have in reality. For overcast and clear sky, there is a better fit. There you can still see the simulation over-predicting the measurement because of the lack of obstruction, but it's much more promising. And once we get through all these refinements and obstacles, as we go over them, we get closer and closer to this representation, closer matching between simulation and reality. And after we get there, there is another factor that will really constitute the next challenge of the project, and that is obviously people. So taking into account the effect of all the people coming in for larger events now that, well, not right now, but hopefully soon again, allowed into the building. And then, obviously, there could be many more research done on the subjective evaluation that these people give to the indoor condition of the building visually and as for other parameters. So that's about it. I owe a big thanks to all the companies involved in the project and to all the people as well. And I just would like to invite you all to visit the building, and if you have any idea for further research into it and you think it's interesting, just come over to Delft and have a look. Thanks a lot.